Some things in our world are pretty simple, right? The temperature is 20 degrees. The pressure is 100 pascals. A single number tells you everything you need to know. But what about the push of the wind on a kite or the pull of gravity on an apple? All of a sudden, one number just isn't going to cut it. To really understand these forces, we need to know not just how much, but also which way. This is where we need a whole new language.
I mean, really think about it. If you push a box, does saying you used 10 newtons of force tell the whole story? Absolutely not. It matters a ton which way you pushed it. Forward, backward, sideways. How hard is only half the picture.
So this key difference basically splits our physical world into two types of quantities. On one hand, you have scalars. These are your simple, one-dimensional values like pressure. And on the other hand, you have vectors, which are so much more descriptive. They've got both a magnitude, that's the how much, and a direction, the which way.
To solve our little pushing problem, we need a new tool. So enter the vector. And the easiest way to think of it is just as an arrow. The length of that arrow tells us the magnitude, how hard the push is, and the direction it's pointing, well, that tells us the direction. Simple as that.
And you know what? Vectors are literally everywhere once you start looking for them. Force, velocity, acceleration, those are the classic examples you learn in school. But they also describe invisible forces, like electric and magnetic fields. Even the simple idea of getting from point P to point Q, what we call displacement, that's a vector too.
All right, so we've got these arrows, we know what they are, but how do we actually do anything with them? What happens when two forces or two velocities start to interact with each other? This is where our basic vector toolkit comes in.
So let's kick things off with the most basic operation you can think of, addition. But here's the catch. Combining vectors isn't as simple as just adding two numbers together. You have to account for their direction, and that's what makes things so much more interesting.
Picture this. You've got an airplane flying east at 500 miles per hour. That's its velocity vector. But then it gets hit by a tailwind. That's a whole other vector, pushing it at 70 miles per hour, but a little bit to the north. So what happens? The plane doesn't just get a speed boost, its entire path gets shifted. Its true path over the ground is the sum of those two vectors, which you find by placing them tip to tail.
Okay, next up in our toolkit is something called the dot product. Now, this is a really special way of multiplying two vectors. And the weird thing is, the result isn't another vector, it's just a single number, a scalar. We get it by multiplying the matching parts of the vectors and then adding it all up. But what on earth does that final number actually tell us?
The best way to think about the dot product is, it's all about alignment. A big positive number means the two vectors are pointing in very similar directions, they're working together. If the dot product is 0, it means they're perfectly perpendicular, not helping each other at all. And a negative 1, that means they're pointing in opposite directions, basically fighting each other. It's like asking, how much do these two forces agree?
And this idea of alignment is perfectly captured by this concept of projection, or you can think of it as a shadow. Just imagine you're shining a flashlight from directly above vector u. The dot product is what helps us figure out the length of the shadow that vector u casts onto vector v. It basically tells us exactly how much of u is working in the same direction as v.
All right, let's move on to the final tool in our basic kit. And this one's a bit of a strange one, the cross product. Unlike the dot product, when you take the cross product of two vectors, you get a brand new vector. And here's the wild part. This new vector is always perpendicular to both of the original vectors. It kind of pops out into a new third dimension.
Okay, so why would you ever need something like that? Well, think about something as simple as using a wrench. You've got the lever arm itself, that's one vector. Then you apply a force at the end of it, that's your second vector. The twisting force that actually turns the bolt, what we call torque, is the third vector that points right along the axis of the bolt. That is the cross product in action, generating rotation out of two other forces.
So, we've got this awesome toolkit for playing with vectors. But what happens when those vectors aren't just sitting still? What happens when they're constantly changing, moment to moment? Well, to tackle that, we've got to bring in the big guns, calculus.
And this, right here, is where vectors go from being a cool math concept to an incredibly powerful tool for predicting the future. They don't just describe a single push or a single pull, they let us predict the entire journey of an object over time, whether it's a thrown baseball or a launched rocket. It's actually an incredibly beautiful process when you think about it. You just start with one simple vector, the constant downward pull of gravity. Then, using calculus, you can add up the tiny effects of that pull over time to find the object's velocity vector at any given moment. Do that one more time, add up all the tiny changes in velocity,
and you get a final vector that perfectly maps out the entire beautiful parabolic arc of its flight.
Okay, so we've seen how vectors can trace a path, like a baseball flying through the air. But let's zoom out a bit, because vectors are also the language we use to define and understand all sorts of complex shapes, curves, and surfaces in 3D space.
And honestly, the descriptive power here is just stunning. I mean, look at these. Complex mathematical knots, or even the very blueprint of life itself, the DNA double helix, can all be precisely defined by vector functions. They're all, at their core, just these elegant paths traced out by a vector moving through space.
Vectors can also help us find our way on complicated surfaces. If you look at a topographic map like this one, every single point on it has a special vector we call the gradient. And that gradient vector always points in the direction of the steepest uphill climb. So if you're a hiker who wants the toughest climb, forget the map, just follow the gradient vectors straight up.
So we've seen the math, we've seen the geometry. For our final section, let's bring it all home and see how vectors are, quite literally, the language that reality is written in.
Deep inside a particle accelerator, scientists use these incredibly powerful magnetic fields to steer particles. The force that the magnet puts on a moving particle is a cross product, and because that force vector is always at a right angle to the particle's direction of travel, it bends the path into a perfect circle. But it never speeds it up or slows it down. It's the ultimate steering mechanism.
And this isn't just for physics, it's happening inside your computer right now. How does an AI get smarter? Well, you can think of it like it's trying to find the very bottom of a huge, complicated valley in the dark. How does it do it? At any point, it calculates the gradient vector, which points uphill, and it just takes a small step in the exact opposite direction, over and over again, until it finds the lowest point.
So what's the big takeaway here? From the flight of a plane to the torque on a bolt, from tracing the shape of our DNA to training artificial intelligence, vectors aren't just some abstract math idea. They are the essential, fundamental language that we use to model, predict, and literally build the world around us.
They really are the unseen arrows that give shape and motion to our reality. And that just leaves you wondering, right? What else is out there? What other complex parts of our world are just waiting for us to figure out the right set of arrows to describe them?